Okay, great. So to give a little bit of background, and I'm not going to introduce what human challenge trials are or what it is that that's happening. The first stage is a dosing study where they figure out how much of the virus needs to be put into somebody in order to check that you can in fact get sick from an intentional exposure, so that if you're testing something with a vaccine or similar, you know that in fact the exposure would work. Given that, the critical question that we have to ask is, how risky is this? And we know that for younger populations, it's less risky than it is for other populations. But in order to do informed consent properly, you need to tell people exactly how risky it is. So if you can go to the next slide. So this is our model interface, and we'll talk a little bit about all of the numbers and what it is that's happening. But the goal is to give people a way to actually explore what the risk is. And the basic question that we're answering is, if you ran a trial with some group of people, what's the probability that somebody would die, or conversely, that nobody would die when running the study? And what's the probability that somebody would have a serious case that would require hospitalization, or what's the probability that nobody would have such a case? And we find that it's very safe, as we kind of knew, but we can give a little bit more detail too. Next slide, please. All right, so we have a pretty looking preprint that is under review, and the preprint discusses the model consisting of 3 parts. So the first part, which Witold is going to introduce, at least starting on the next slide, is the actual model that does the calculation to figure out what it is we think the risk is. On top of that, we have a fairly straightforward calculation to figure out if the risk for one person is at some level, then the risk for a group of n people is, and you can simulate that pretty straightforwardly if everybody remembers their probability theory classes. And then we have a front end that lets potential volunteers and policymakers look at what the risk is and understand how that changes if you use a different age group, or if you make slightly different assumptions about the risk. So next slide. Okay, so Witold, I believe this is.
Yeah, that's me. Hi, everyone. I'm Vito Vinsec. I am a mathematician and researcher based in London, and since at some point this summer, I've been working with One Day Sooner on finding an appropriate model for risk, in particular the risk of mortality, although I think we'll mention how this can be extended to other outcomes related to COVID. So I just wanted to give a few minute overview of how do we arrive at those numbers that you've just seen in the dashboard that David had, and why are we confident that this is roughly the right number. So the centerpiece of this modeling approach is meta-analysis, which is, I think, a term that everyone is familiar with to some extent. This represents a golden standard for synthesizing evidence from many studies. In medicine, this can be randomized controlled trials. It can also be observational data, like we have with COVID, where many different countries will report mortality rates and some estimates of how many people already had COVID. So the crucial quantity that we're working with is IFR, infection fatality rate, which tells us how many of people who were infected with COVID are going to die. This, of course, is going to vary from place to place and from person to person. In particular, we know that this is all about age groups, right? So we know that to arrive at a good estimate that we can have some confidence in, we have to combine across as many studies as we can to take account to take heterogeneity into account, so how much studies differ from one to the other. And we also have to do it because while there is it seems, data from practically every country in the world on mortality, etc., there is relatively little good data on mortality in younger people and healthy people as well, right? Because mostly most of reporting will focus on people who had some underlying conditions, etc. Technically speaking, to do this, we use Bayesian statistics. And in particular, if anyone is technically minded, we can come back to this. We use Stan modeling language to create this model. And we'll say a few words more in a moment on that. This model, other than taking into account likely ranges for how many infections happen and how many deaths happen, also takes into account things such as age. And crucially, we use this model to also incorporate data for certain age ranges in certain countries where no deaths were reported, so that we don't accidentally overestimate risk due to COVID. In many countries, if we look at ages 10 to 20 or 20 to 29, at least in certain subgroups, certain regions, no deaths were actually recorded, at least at the time when many studies were published. We take that into account as well. So we model all of the ages, but we pay extra attention to younger people, as these are the groups who would participate in a human challenge trial. So by this we mean 20 to 29 or possibly 20 to 39. And then on top of that, in our model, we will also include some adjustments for no comorbidities, and the fact, as we mentioned, that many different countries and many different populations means that the risk will go up and down across them. So we can also learn something from that. Can we see the next slide, please? Okay, so I'll just very quickly, so that people can have a bit of an idea for like what is it actually that we do in practice. This is one of the main visuals that we have in the paper we submitted. Left and right panel, they actually show the same thing. It's just that the scale changes. You'll see that on the left, the y-axis is actual percentage points, or sorry, it's just percent or a fraction. And on the right-hand side, we use the log scale. And we use this log scale because, as you can see, while this risk grows exponentially, the y-axis is infection fatality rate, it rises exponentially with age. Therefore, you can actually put it on a line as soon as you take a log. So the main conclusion from that is that actually, once we can fit this model to data that was observed, is that the risks become near negligible, with exception of infants, as we get younger. And what we see here is the shaded gray areas are actually what the model predicts. The red points are individual studies, individual countries, individual populations for which data was reported. We can come back to this if people have questions. Next slide, please. Okay, so what are the conclusions from doing this meta-analysis exercise with our own Bayesian model? We find 1.7, 1.8 actually, I guess if you round it, deaths per 10,000 infections in this crucial 20 to 29 age groups. Our estimate is, it's a statistical estimate, so it's nothing is 100% certain, but we are 95% confident that this number is somewhere between 1.3 and 2.4. I would call it quite precise. Risk in people who do not have comorbidities is, however, 1.88 times lower. So we could translate this overall to saying that we would expect to see 1 death per 10,000 infections in the 20 to 29 age groups. However, this is not to say that this is our estimate of what would happen in human challenge trials. This is based on observational data from many countries for what actually happened in the real world. If we wanted to make some assumptions about how much human challenge trial can reduce risks, we could at least look at how low the risks can be in certain populations in the real world, in certain countries at certain time. Therefore, by conducting this extra analysis, we find that the risk can be as low as 3 deaths per 100,000 in some populations. But of course, we would have to explore further what drives these differences. Last 2 comments would be that this model that I just described, it is fully transparent. So not only it is submitted as a preprint, but all of this is online for everyone to see. All of our data is out there. All of our model code is there if someone wants to run it. And we do it also because we hope to have this estimate changing over time as more data becomes available, and possibly as we can model more outcomes. Lastly, the number that I've just given, the headline number of 1 death per 10,000 infections, this totally agrees with other published literature. There is of course small differences because they use slightly different data sources, they use slightly different methodology, but qualitatively this is all in agreement. Okay, that's it from me. Next slide.
Yep.
Oh yeah, go David.
Okay, so the piece that's important for assessing risk is knowing what the risk is. The piece that's important once you're done with that is making sure that people understand what the risk is. So the first piece of that is the interactive model, which we think that research has shown actually, people are much more comfortable with understanding risks when they can play with the model and see how it varies depending on other factors. And we hope that it allows people to do that, to kind of get a better grasp of what it is. Specifically, we have comparisons to other risks. And if you saw at the top, comparison to how risky liposuction is, which is relatively safe. We're certainly comfortable letting people choose to get liposuction, even though there are some risks. And depending on exactly how risky the model says that the particular population, the particular assumptions that you're making are, that the comparison risk changes. And then we also have a graph of the risk compared to a number of other types of events that we think are useful to understand how risky participating is. So the kind of final takeaway we hope people have is the risk is, as we have long been reasonably confident, the risk is low, and we think that the risk, at least of mortality, which is not the only risk that we need to worry about, and we have a link to discuss long-term risks, and we also talk about hospitalization as kind of a proxy for the disease can be serious enough that somebody is sick for multiple weeks, even if they fully recover, or in some cases take a long time to recover. It's the risk is still fairly low, and we can show that. So that's kind of what we're hoping that the model can help explain to people. And I think that that's it for what we wanted to say. We'd be really happy to get the next slide. We'd be really happy to get questions from people about what it is that they think, or questions that they have about either the risk or the model or what it is that we're planning to do to update it and continue.
Thanks so much.